Welcome to qnawire.
Here we're going to use a large sheet of uniform charge in order to suspend a small charge of charge Q, mass M above. So there are a couple things that we're going to need. One, we're going to assume that the sheet is large enough that it creates a uniform electric field that you could determine through the use of Gauss's law. So that's the first assumption we'll use. And based on that, the E will be directed, let's give some dimensions here. Let's call the Z-axis pointing straight up. So the EZ is constant in magnitude and equal to sigma over 2 epsilon naught. The second thing that we'll need, and we can calculate that later, but the second thing we need is Newton's second law, which says that the sum of forces on an object is equal to mass times acceleration. And here we want to hold that charge in equilibrium. So we will set that equal to 0. Coming up with a free body diagram on that charge, what we are assuming is that it is sitting in a uniform electric field that points up to the positive Z and is the same everywhere. Yeah, I'm going to stop drawing these. Uniform. And the charge then will feel an electric force upwards equal to Q times the electric field in the Z direction. And like usual, there will be weight downwards. And we must have those things equal to each other. What we are after is what charge should we use in order to keep that little charge just hanging there suspended by the very large electric field underneath it, or the electric field, I should say, of the large sheet. We'll see how large the electric field is by doing a calculation. So we'll use SI units, which would be coulombs per meter squared for the charge density, surface charge density. And we would want the permittivity of free space, the epsilon 0, also to be in SI units. 8.85 times 10 to the minus 12 SI units, which would give us the electric field in newtons per coulomb. And we do get a fairly large electric field in the Z direction. So now using Newton's law, we want to balance the upward force with the downwards weight. And then we can very readily solve for the Q. We know the mass of the charge in SI units, kilograms. And we certainly know G, so we can find the weight in newtons. And then we must divide by the electric field in the Z direction, which we now have calculated. And we wind up with the amount of charge in coulombs. And I will write that as 0.278 nanocoulombs, where nano is 10 to the minus 9. Now notice that we never used the distance above the sheet. So we were starting with the distance of 1.5 centimeters. And then the question is, what if you had used 3 centimeters? So here we are assuming that the charge is close enough to the center of a very large sheet that we can ignore edge effects. So the idea is that the electric field in the z direction is uniform, and so the amount of charge does not depend on distance, at least for the assumptions we have made. At some point it will make a difference, but without knowing the dimensions of the sheet, we cannot say anything extra.